In this video, we're going to look at two applications that involve line integrals. We're going to look at work and circulation. I want to do a very quick review of work done by a force. This is a very common application for line integrals. My vector field may be a force field, and if I use line integrals with this force field, I can compute the work that's done on an object that is moving in that force field. If F is a constant force field, the work done in moving an object a distance d along the x-axis is given by W is equal to F sub x d, where F sub x is the magnitude of the force times the cosine of theta, where theta is the angle between the direction of motion and the application of the force. Only the component of F in the direction of motion actually contributes to work. And if the force F is a variable force field, the work done in moving the object from x is equal to a to x is equal to b is given by W is equal to the integral from a to b of F sub x of x dx. This is the component of force in the direction of motion, which in this case is parallel to the x-axis. Now I'm going to extend these ideas into multiple dimensions. Let F be a continuous force field in a region D of R3, and we'll let C be the vector R of t given with components x of t, y of t, z of t. For A is less than or equal to t, which is less than or equal to b, and it is a smooth curve in D with a unit tangent vector t that is consistent with the orientation of C. The work done in moving an object along C in the positive direction is given by W is equal to the line integral over C of f dot t ds, which is equal to the ordinary integral from a to b of f dot r prime of t dt. Let's work an example. If I'm given the force field F, I want to find the work required to move an object on the given oriented curve. The force F is equal to the vector with components x, y on the path consisting of the line segments from the point -1, 0 to the point 0, 8, followed by the line segment from the point 0, 8 to the point 2, 8. I have two paths here. There's an R1 path, r sub 1 of t, which is given by the vector -1, 0 plus t times the vector 1, 8, which is equal to the vector with components t minus 1 and 8t. R sub 2 of t is equal to the vector with components 0, 8 plus t times the vector with components 2, 0, or the vector with components 2t and 8. These are both paths in which my parameter t will lie between 0 and 1. So that W is the line integral over C of f dot t ds, which is equal to the sum of two ordinary integrals, the integral from 0 to 1 of f dot r sub 1 prime dt plus the integral from 0 to 1 of f dot r sub 2 prime of t. This is equal to the integral from 0 to 1 of the vector with components t minus 1 and 8t dotted with a vector with components 1 and 8 dt, plus the integral from 0 to 1 of the vector with components 2t and 8 dotted with a vector with components 2, 0 dt. This is going to be equal to 69t squared over 2 minus t evaluated from 0 to 1. This gives me 69 over 2 minus 1, or 67 halves. Now I want to talk about circulation of a vector field. Circulation is a measure of how much of a vector field points in the direction of C, which is a closed, smooth-oriented curve in D. You can think about it like walking in a windstorm. On part of the path, the wind is blowing directly into your face, slowing you down. On the other parts of the path, the wind blows directly at your back, helping you move faster. The circulation ends up being the net amount of time that the wind is moving in the same direction with you. It can be positive, negative, or zero. So if I let F be a continuous vector field on a region D of R3 and let C be a closed, smooth-oriented curve in D, the circulation of F on C is given by the line integral over C of F dotted with T ds, where T is the unit vector tangent to C, consistent with the orientation. So, do you notice anything? This idea of line integrals just keeps cropping up in all kinds of problem types. The key here is to pay attention to the context of each problem and understand how the line integral will inform you about the problem. It's like a hammer in a toolkit. You can use it to make a bookshelf or build a house. Same tool, different problems, different interpretation. Let's work another example. I want to consider the given vector field F and the closed oriented curve C. I want to make a conjecture first about whether the circulation of F on C is positive, negative, or zero. And then I want to compute the circulation and interpret the result. I'm given a force field with vector components y minus x and x, and I'm given an oriented curve given by r of t is equal to the vector with components 2 cosine t, 2 sine t, where 0 is less than or equal to t, which is less than or equal to 2 pi. The first thing I want to do is observe what's happening in my vector field. By observation with this vector field, I can see that the vector field moves in a clockwise direction and a counterclockwise direction in about equal proportion inside my closed oriented curve. If I'm moving in one direction half the time and the opposite direction the other half of the time, the net is going to be zero. So I'm going to anticipate that my circulation is going to be zero. Let's evaluate the integral and see if we're right. My line integral over C of f dotted with t ds gives me the ordinary integral from 0 to 2 pi of f dotted with r prime of t dt. This gives me the integral from 0 to 2 pi of the vector with components 2 times sine of t minus cosine t and 2 cosine t, dotted with a vector with components negative 2 sine t, 2 cosine t dt. This gives me negative 4 times the integral from 0 to 2 pi of the quantity cosine squared t plus sine t cosine t minus sine squared t dt. This gives me negative 4 times the quantity sine of t plus 1/2 sine squared of t evaluated between 0 and 2 pi. When I plug in my limits of integration, my result is 0, so that my total circulation on this oriented curve is 0. Now you get to try it. Pause the video and find the work required to move an object on the oriented curve C for the force field given by F is equal to a vector with components negative y, x, and z on a helix that's given by r of t is equal to a vector with components 2 cosine t, 2 sine t, and t over 2 pi. For 0 is less than or equal to t, which is less than or equal to 2 pi. When you're ready, restart the video to check your understanding. So my work will be given by the line integral over C of f dotted with t ds. This will be equal to the ordinary integral from 0 to 2 pi of f dotted with r prime of t dt. My r prime of t is given by a vector with components negative 2 sine t, 2 cosine t, and 1 over 2 pi. So that my ordinary integral from 0 to 2 pi of f dotted with r prime of t dt becomes the ordinary integral from 0 to 2 pi of a vector with components negative 2 sine t, 2 sine t, and t over 2 pi, dotted with a vector with components negative 2 sine t, 2 cosine t, and 1 over 2 pi dt. This simplifies to the ordinary integral from 0 to 2 pi of the quantity 4 plus t over 4 pi squared dt. This gives me 4t plus t squared over 8 pi squared evaluated from 0 to 2 pi. I plug in those limits of integration and I end up with 8 pi plus 1/2. This is how we work with work and circulation using line integrals. Be sure and let me know if you have any questions about working in R2 or R3 space with these work and circulation problems.